So you know by now that I'm building a super cool motorcycle. I mean, it's just like a fact at this point. Actually, I'm trying to build a Honda Goldwing bobber. Now, I'm not the first to do this, but I do think it's a very cool project. This is a cool modification for a Goldwing. And in all honesty, there is a guy in El Paso with, I believe, Cool Monkey Garage that has done several of these, and I'm highly influenced by his work. So, all credit due to that guy. But I don't know his name, so if anybody knows the name of that guy. Now today, I want to talk about suspensions, specifically the rear suspension on this bike. This bike. On the stock Goldwing, it has twin shocks, meaning a shock on either side of the bike, just sort of behind the rear seat. I'll show you. There's a shock right there. So there's two of them, one on each side, approximately right there. Well, exactly right there. So you can see on this guy that on the swing arm, that's that guy right there, the shocks mount, they're exactly 3 inches from the wheel axle, which is like that bolt right there. That's the axle that goes all the way through the wheel. And so that's where they're located on a stock suspension. And the swing arm can be thought of as a lever in terms of understanding how a suspension works. It runs from up here, where it connects to the frame, all the way down here to where it connects to the wheel. That's one big lever. It moves, right? And so any lever has basically a pivot point, like a fulcrum, and that's this point over here. It connects to the frame, and that's where it pivots. It goes up and down. This swing arm moves up and down off of this fulcrum point. And so my plan involves moving these shocks further up the lever over into here somewhere. What this does in terms of the physics and engineering, it presents a problem. You can see here that the springs have that much amount of compression. That silver strut part on the inside there, that shaft, that is what compresses. That essentially represents the compression amount on this shock, how much it will compress. That's about 2.5 inches on this particular shock. I move this guy into here. Important part is that I move it further up this swing arm. Now, 2 inches here, I calculated it results in about 3 inches of travel here. So the wheel in total moves 3 inches on a stock bike. This is important, especially on this bike, because if we go to the other side, this bike has got a drive shaft on it. And so this drive shaft functions as the swing arm on this side, and it goes all the way up here to this part. And then this is the universal joint right here where the drive shaft connects directly to the transmission on the engine. This joint can only handle so much movement. It's only designed to handle so much range of movement. The greater the range of movement, the more stress is going to be put on that universal joint, and the quicker it's going to wear out. When I'm modifying the suspension, I want to stay within, ideally, the manufacturer's, the stock wheel travel. I want to keep this wheel travel as close to the stock range as possible. All right, so by moving the shocks from here all the way back to here, I calculated it out. I will theoretically have a wheel travel, this guy here, of 12.5 inches, which is, holy crap, way more than what I or that universal joint over there want. So that's not good. That is a problem. But this brings up the question, is that really the case? Because other people have used that design, essentially. They just move the shock forward and have run the bike that way. It must work, right? Well, maybe it must. I don't know. But that was a question that my curiosity just had to answer. And so the only way I know how to answer that is through math and calculations. And so I did my best. I'm not a mathematician, but I did my best on this. See, if I use the stock shocks, these guys, which are designed for a bike that by itself weighs 730 pounds, and I move them forward up here, and then through some chopping, like we talked about in a previous video, chopping off a bunch of this metal and a bunch of all the fairings and all this stuff, I get to a point where the bike theoretically weighs about 450 pounds. Well, now there's another math problem. This problem involves figuring out the forces exerted by a lever. Which lever? This lever, this swing arm right here. It exerts different forces at different points along it. The forces come from this wheel pushing up, right? The fulcrum down here, this guy, that's the swing arm axle down there. That's where it moves. That's where it joins the frame, and that's where it rotates. So this whole guy here is a one big lever. So now I've got to determine, can I use these shocks if I move them up there? Because I've reduced the weight of the bike. Are they still somehow usable? One of the main things that I stumbled upon and I learned this week is that spring rates. The spring right here has a specific rate, they call it a spring rate, and that is how much weight is it designed to handle in order to operate within a normal range for the shock. Spring rates are described in terms of like force per distance kind of thing, where you've got pounds per inch and kilograms per millimeter. Those are the common terms that are used for spring rates. I would like for these shocks, if I move them up here, to operate at a somewhat normal spring rate, which should give me a somewhat normal suspension and a decent ride. That's the goal here. So, using some rough figures and at the same time trying to customize this to my specific weight, the bike, if it weighs 450 pounds when we're done, and that's our best guess, plus 200 pounds for a rider, that's 650 pounds total. Then if we make the assumption that half of that weight is going to be held specifically on this rear wheel and half on the front wheel, which is a decent assumption. It may not be accurate entirely, but we should be hopefully close. Half of that 650 is 325, right? So using a formula for, and here's the correct term that I discovered this week, for a third class lever, which I found that formula on a website called Engineering Toolbox, and I'll put a link to that in the description of this video. I then determined that if I move these springs, or if I had springs right over here, whether these ones are different ones, if I have springs at this point on this lever with the force being way out here and acting upon the spring way back here, that spring or springs, they'd be handling a force of 1,500 pounds. And so they would have to handle a force of 1,500 pounds right here in order to be able to hold the bike up and operate. I then found a spring rate calculator, a website called hypercoils.com. I'll also link that in the description of this video. This is just a super value video. I've got so many links in the description. Using their calculator, I was able to determine that I would need a spring or springs with a 660 pound spring rate. And then out of curiosity, I went back and sort of re-engineered or redid the math on these guys at a stock location so I could figure out what the spring rate is for this spring. And these should, both of the springs together, there should be a spring rate of 185 pounds. So if you divide that by 2, you get the spring rate of each shock here. And so with that information, moving the shocks over here, we now know would add about 3.5 times the force to the shocks. All right, and so because this is hoopty-doodle, I don't want to spend hundreds of dollars, if not thousands, on getting a custom shock made to fit over there. So the solution, of course, is to buy a used shock off of another bike. All right, I can't use these shocks. I need different shocks. Get a used shock off a different bike. Now I've got to find a shock with a 660 pound spring rate to go in there, right? It's a simple solution at this point. All I need is that shock with the correct spring rate. But wait a minute, we still have the wheel travel problem. And that sounds simple, to locate a shock with the correct spring rate. However, it's not. It's really, really difficult from what I have found. I looked far and wide on the internet and I could not locate manufacturer shock spring rates. They don't provide them, basically. And so the best resource I was able to find was another website. This is more value to this video. Another website, I'm gonna provide another link to another website in this description, is racetech.com. That's in the description. And so Racetech is a company that makes custom shocks. And so they've very nicely, whichever nerd over there at Race Tech, I want to thank you, because even though you don't have, spring rates for every stock bike out there, you have spring rates for quite a few, and enough spring rates that I could make this project work for me. And I really appreciate that, because this was a major problem that was driving me crazy trying to figure out. So anyways, they have a search tool over there on their website that allows you to search specific bikes. Like you can look up a Ducati, Monster, 900, whatever, and it will tell you, if they have the information, it will tell you what the spring rate for the stock spring on that bike is. That's the best source I could come up with to find spring rates for stock bikes. So most of the shocks that they have on there, because they're only for those types of customers that have custom shocks made, they only have information on bikes that those customers owned. And so most of those customers, as you would guess, if you thought about it, are people who race bikes. And so they've got a lot of dirt bike information and a lot of sport bike information on there for shock rate, at least for the rear shock rates. I didn't pay any attention to what they had for front shock rates. For instance, on there, one of the things was a Honda CBR 600 RR. They had a rear shock rate for the stock shock on that. It was 610 pounds. And so it was close to what I was looking for, right? It was very close to the 660 that I was looking for this build. And so another glorious moment I had was that I realized that on eBay, these CBR 600 shocks are cheap. They're some of the cheapest shocks on there in terms of used shocks. I could get one for like less than 50 bucks, which was pretty sweet. Now the wheels are turning. How do I engineer this swing arm to make the shock off this CBR work? And quick side note here, another consideration was that the swing arm possibly would be, because the drive shaft is on one side of the bike and whatnot, I don't know, it could be subject to additional torque from the drive shaft that could affect, because I've chopped off all this stuff, it could be subject to more torque on the swing arm and the rear axle and everything. Basically, mainly on that rear axle, that there could be more torque on that. I don't know that that's true though, because I started to think about it. I mean, somebody brought that to my attention, and I started thinking about it, and I was like, what's preventing there being torque on it now, right? In its stock form, what prevents that swing axle from torquing? The shocks are the only thing I'm removing that help reinforce that swing arm. They're the only thing I'm moving. And the shocks themselves are designed to move. They're not exactly going to prevent torque. They might provide some resistance, but it didn't quite make sense to me. It still doesn't make sense. And if it does to you, please let me know. But and explain to me how does that affect it? And is it a major consideration? Because I don't think it's a major consideration. I don't think it is. I think it might be a minor consideration. I can't imagine that the swing arm and the swing axle aren't over-designed, over-engineered to some degree to handle more torque than what they have in the stock form here. And so I think I should be safe as terms of that goes. But hey, I'm not an engineer. I'm not a mathematician. I'm just a guy who's willing to try. So after a lot of thinking, like days of thinking, like I don't think that fast, and so after a lot of thinking, a lot of time spent thinking, I started to settle upon the idea that I needed a cantilever swing arm design, which means basically you've got your swing arm and then you add onto that swing arm this sort of triangle thing on top of it, and that helps to provide that basically in my situation here. Let me take you back to this swing arm. All right, and so if we're looking at this swing arm, modifying this existing swing arm into a cantilever type swing arm, basically what I'm going for here and what the advantages of it are, a cantilever is basically, if you imagine a triangle up on top of this existing swing arm just added to it, that would essentially make this into a cantilever style swing arm, because at the peak of the triangle, right about here, right here, that's where the shock would attach, and it's from that point the forces would be going through there and then being distributed down to the swing arm over here. And by doing that, and by picking the point along this swing arm at which that force is distributed down onto it, I can sort of fine tune to some degree the amount of force that is being transmitted up into the bike. Meaning I can dial in to some degree the spring rate that I need for the shock. Oh, honey. All right, and this concept was like just, whoa, look how powerful math is, like awesome. And with this concept in mind, I went back to calculating the final design for the suspension. And I immediately ran into problems with wheel travel. I just couldn't get the wheel travel where I wanted it to by using a cantilever swing arm design. I just couldn't. I could get it down to about 6 inches of wheel travel, but that was it. So, having exhausted all possible combinations and design combinations of a simple cantilever swing arm suspension design, I had to go look for other solutions. I was forced to look at a modern style suspension, which modern style suspensions are linkage suspensions, most of them. That's the main one. And there are several types of linkage suspensions, several names, several different attempts at branding and redesigning and coming up there with your own special linkage design. But essentially, they're all the same basic concept of adding more levers to the suspension. And so we all know the power of levers. They are great, and they're really good for solving suspension problems, apparently. Basically, with a linkage system, the shock is not the direct point of contact between the swing arm and the frame. The shock is not the only thing that's in there. You've also got the linkage. The linkage is in there too. Another lever basically gets put in there, at least one. Some bikes have designs with more than one lever in there. But me, being a simpleton, I want to minimize the number of levers in there so that I can comprehend what the heck's going on. If you look at a modern linkage suspension style on a bike, like on a Ducati or like a Honda, any of those bikes that have monoshocks on them, a new one in a showroom, go look at those. They're cool looking, man. There's a whole kinds of mechanical things moving, and they just look like some designer went crazy. Not even an engineer, but some designer, because they just look mechanical and like steampunky, you know? There's a lot of stuff going on there. But if you don't know what you're looking at, it's really intimidating. And so I was really intimidated because I don't know what I'm doing. I didn't know this whole week I've just been learning about suspensions. I didn't know anything about suspensions essentially and how the physics of them worked, you know? I didn't know anything about that at the beginning of this week. And so that's why I resisted looking at these more complex systems to begin with. And, you know, why start with complex? Why start there, you know? I ended up there because I ran out of options on the simple end. And so now I'm going to the complex, more complex as needed. And so looking at these, I was like, oh my God, how do I even do the math on this? Now there's more than one lever going on. There's all these moving parts. What are these moving parts, you know? And then I realized the solution started to appear as soon as I realized that all these moving parts are just more levers. They're just adding an additional lever. And that lever is attached to another, like one lever, the swing arm, has another lever on it, which is then attached to the shock over here. And so all this lever, you can just distribute the forces from one lever to the next when your calculations. If you do your calculations one lever at a time, force is distributed from here to here on this lever, and then from that point, I take that amount, whether it's 1,500 pounds or whatever, and I start on my calculation for this lever, and I start with 1,500 pounds. I do the calculation until I get my other number on that side of the lever. Once I figured out how to do it, it was really not that hard. And so at this point, I had done several dozen calculations on levers. And so I was fairly quickly able to determine that a linkage system was indeed the solution I had been hoping for, or at least I hoped it was. I started out thinking that I would utilize a linkage. I would put the shock on one side, and I would put the swing arm on the other side, essentially. And in the middle, I would have, as the fulcrum, I would have the frame of the bike. As the suspension traveled up, it would push down on that shock over here. Push that sucker down. And then once I had this concept of the fulcrum and this lever in mind, and how adding force on this side would affect force on that side, and then if I had a huge breakthrough when I realized that if I changed the length on this side from here to here, I could change that length, customize that length right there in proportion to the length over here from the swing arm to the shock. I could customize the lengths in between those so that if I had twice as much length over here as I did over here, then the forces would be reduced over here. Over here, the forces would be reduced by half. And that was a breakthrough for me. That allowed me to go, oh, I can customize, I can really dial in the spring rate now. But still, there's limitations to that. I could only dial it in so much with my simple brain. Only so much. I could dial it in to the point where I discovered that a Honda CRF like 450 had a spring rate of exactly what I needed. If I did this in a 2-to-1 ratio, where there's twice the length here and as over here, then I could reduce the spring rate over here to exactly like 5.2 kilograms per millimeter. I forget what that translates into in pounds, sorry. And so I could dial that in right there. And so then I would end up with that, and that was exactly what the spring rate is for one of those Hondas. And but the problem is that Honda, that specific model with that specific spring rate, that was a dirt bike. And dirt bikes are great, but the only problem was that the shocks on those have a longer travel to them, which would affect my wheel travel to some extent. It was mainly a problem in that shock was so long. The shock was so long that I wouldn't be able to fit it in the frame of the bike. It was 18 inches long, and so that created another problem for me. So I was really close though. I had a suspension design that would allow me to minimize the wheel travel to where I wanted it, which was about 4 inches. And then it would also allow me to utilize a stock spring off another bike that was readily available. Those were my two major things that I wanted to, but I was really close at this point to getting it right, but it wasn't quite as eloquent of a design as I needed because I knew installing that shock and making that fit was going to be a hassle. So I had to, again, redesign the suspension. And so going back to the internet, I found some pictures of the rear suspension linkage on a Ducati Panigale. And I was really inspired by that because what that suspension did was that it took this linkage, and I had it designed so that I had the frame as the fulcrum right here. They put the spring right here. The shock was in the middle, and then they had frame and a swing arm on different ends. And so you could still manipulate the lengths here to control for wheel rate. I could still do that. And to conceptualize that, I really had to think about, I had a hard time with that at first, because now we got the spring, and the spring is going to give to some extent. But once I conceptualized the idea that this spring was still the fulcrum between the frame over here and the swing arm over here, this was still a fulcrum point. It still would affect the wheel rate the same way. At least I think it will. I could be totally wrong, but I'm pretty sure I'm onto something at least here. I'm going with it. And so I could keep my 2-to-1 ratio, keep my wheel travel, which is also known as wheel rate. I could keep that wheel travel where I wanted within that 4-inch range, and then I had the shock here. So 5.2 kilograms per millimeter is a lower spring rate. That is, a dirt bike has a softer suspension on it because it's meant to travel a lot and hit some huge bumps and all that stuff. Dirt bikes have softer suspensions on them for that reason. So road bikes, street bikes have harder suspensions on them. What happens when I move the shock in on that lever, that linkage there, is that then the forces acting upon it are greater. They increase. And so what happens is that I need a harder spring. And you know what types of bikes have harder suspensions? Street bikes. Race bikes specifically have really hard suspensions because they're sport bikes. They're designed to be raced, and you want a more aggressive suspension if you're racing. So lucky for me, I moved this in I needed a higher spring rate for that design, and the CBR had a higher spring rate. Exactly the spring rate I needed. And so I was able to use the spring off a CBR for my build. Oh, I've worked all week on that, like all week trying to figure that out. So, boom, we're stoked that that's finished. Now we can move on to other things, like ordering parts. So the first part I ordered was that spring, that shock. I ordered a used shock off of eBay, and it came with some linkage still on it. So I'm gonna see, like that linkage system, the part of the linkage had that sort of 2-to-1. It looked like it had a 2-to-1 kind of ratio on there, and I'm hoping I'll be able to use that part of the linkage on my bike. That would just make things a little bit easier. So that is my story of the suspension. Keep in mind that I am not an engineer. I don't know what I'm doing. I literally just taught myself this week how suspension forces work, and I don't know how good of a job I did teaching myself. So keep this in mind, because I could be completely off on my calculations, or I could just be slightly off somewhere in the beginning, which leaves me completely off at the end. However, I have checked my numbers, and I am confident that they are correct. Or I wouldn't say, even I wouldn't say correct. I am confident that they are close enough. I should end up with a ride that is very close to what it should be, what a normal bike should be. And I'm confident enough that I went ahead and purchased a shock to move forward with the suspension build. Still have that thing in my brain, since I don't have formal training in engineering, that I could be wrong, that I could be missing some crucial consideration in this design. But I think I've accounted for most of the major factors and enough of the factors in general that I should be safe. I should have designed a safe suspension at least. And I think, I truly believe at this point at least, that it should be really close to a normal suspension ride and quality. And I should have a nice, maybe I shouldn't say nice, but I should have a decent ride when I'm done. And how nice would that be? If you have watched this far into the video, congratulations. You are a super auto nerd, and I love you and I appreciate you, and thank you for watching. Treat yourself to something nice. Subscribe to the channel. Thanks for watching, and we'll see you next time.